Let's use the integral test to determine whether a series diverges or converges. So let's start with a series that we're familiar with, which is a sub n is equal to 1 over n. And by using an integral test, let's determine whether this series converges or diverges. So we already know that this diverges, but let's prove with an integral test that it does. And then also I'll show you why we can use the integral test for many different series to prove whether they diverge or converge. Okay, so first of all, let's go ahead and graph the function 1 over n, or 1 over x. We can do so by graphing n as our x-axis and 1 over n as our y-axis. So let's do that. So this is our y-axis, which is 1 over n. This is our x-axis, which is n. So let me label that as n. This is 1 over n. So we want to find the infinite summation of a sub n from n equals 1. So from n equals 1 to infinity of 1 over n. So we're going to start at 1 for this function. We know that at 1 is at 1, and then at 2 it's at 1 over 2, and it just starts decreasing. So let's draw this out, something like that. And if we take the integral of the function 1 over n from 1 to infinity dn, let's think about how these two are related. How is the summation of 1 over n from 1 to infinity related to the integral of 1 over n from 1 to infinity? And if you recall, to take this definite integral from 1 to infinity, we need to do an improper integral. So if you haven't seen that video, go ahead and watch that. Okay, so let's write out what the infinite summation of 1 over n is. Well, first of all, the first term we have is 1 over 1, which I'm going to write as 1 times 1, and I'll show you why in a second. The second term we have is 1 over 2, which is 1 half. I'm going to write it as 1 half times 1. Again, the times 1 doesn't change it, right? And I'll show you why I'm doing that in a second. Third term we have is 1/3 times 1, and then we have 1/4 times 1. Okay, let's think about what happens if we split this area under this curve. So let's find this area under this curve with Riemann sums, with delta x's that are 1. So delta x is 1. Delta x is 1. Well, the first value of our function would be at 1. So if we draw a rectangle like this, it would look something like that, with the delta x 1. The second one would be the function value at 2, which is 1 half, and then so let me do that in a different color. And then again, our delta x is 1, so the rectangle would look something like that. And once again, this is 1. The length of that is 1. And then our third one would be 1/3. Our value of 1 over n would be 1/3. Delta x would again be 1, and it would look something like that. Now, the reason why I wrote this as 1 times 1 plus 1 half times 1 plus 1/3 times 1 plus 1/4 times 1, etc., is because this is the area under this curve using Riemann sums all the way to infinity, right? So plus dot dot dot. So 1 times 1 would be the area of the first rectangle, which would be delta x, which is 1, times the height, which is also 1. That's why I wrote that as 1 times 1. The next one is, again, delta x, which is 1, and then the height, which would be 1 half. So this would be the area of this rectangle. And so the infinite summation of 1 over n, is technically using Riemann sums to just find the area, or to find the area or an estimate of the integral from 1 to infinity of 1 over n. So what we know about this summation, or this Riemann sum, is that the rectangles are actually overestimating this area, right? We know that if we keep drawing rectangles with the delta x of 1, then this will be an overestimate, right? Because this part is sticking out, so it's going to be greater than what the actual area under the curve is. So we call this an overestimate. So what we can say is that the summation from n equals 1 to infinity of 1 over n is greater than the integral of 1 to infinity of 1 over n dn. Again, let's think about why this is one more time. So we said that this infinite summation is basically just is basically just finding the area under this curve using Riemann sums with delta x1. And we drew it out, we drew a few rectangles out, and we noticed that if delta x is 1 and we use Riemann sums, then our area is actually an overestimate of the actual area, which is determined by the integral. So therefore, this is greater than the integral. Okay, and let me show you why that's important. Well, if we actually evaluate the integral using improper integrals and we get some value that diverges, that means that some value greater than a divergent value is also divergent. And again, that might sound complicated, but let me show you what that means. So let's just evaluate the integral from 1 to infinity of 1 over n dn. Let's see what happens. Well, if you have the integral of 1 to infinity of 1 over n dn, we can rewrite this as the limit as n, again this is an improper integral, right? So we have to write it with limits. The limit as n goes to infinity of the integral of 1 to n of 1 over n dn. Okay, well, what's the integral of 1 over n? That's just the natural log of n, right? So let's rewrite this as the limit as n goes to infinity of the natural log of n from 1 to n. From 1 to n. Okay, now let's evaluate this at those 2 points like we would for a regular integral, and then we'll evaluate the limit that we have. So this is equal to the limit as n goes to infinity of the natural log of n minus the natural log of 1. So I'm going off the screen a little bit, but we're just evaluating at n and 1. Well, the natural log of 1, that's just 0. So we can rewrite this as the limit as n goes to infinity of just the natural log of n. And what's the limit as n goes to infinity of the natural log of n? Well, this is just equal to infinity, right? The natural log of any large number just keeps getting larger and larger and larger. So the limit as n goes to infinity of the natural log of n is just infinity. So this integral, the improper integral from 1 to infinity of 1 over n dn is infinity. Or in other words, we could say it diverges, right? It diverges. And remember we talked about earlier, we said that this summation is greater than this integral. So if this summation is greater than this integral, and this integral is already infinity, then that means this summation is for sure infinity, right? So for that reason, this summation also diverges. So we determined that by using an integral and comparing it with the integral.